to start with, I'm going to turn our attention to change that happens at the surface of the Earth due to interaction of the rock with the atmosphere, with rain, and with living organisms. The change that takes place when rocks interact with their environment at or near the Earth's surface is called weathering. Weathering can happen in two different ways. In some cases, weathering is simply the physical breaking down of larger rocks into smaller pieces. That process is called mechanical weathering, or sometimes physical weathering. It can happen because rocks are cut up at joints and the rocks break apart on joints. Or it can happen once the rock is weakened and the bonds of cement that held grains together weaken enough so that the grains just fall apart and the rock disintegrates. Chemical weathering, in contrast, is due to the chemical reaction of rock with its environment, specifically with air and with water, or with water solutions. We'll see that several different reactions are involved in the process of chemical weathering. It's important to point out also that chemical weathering and mechanical weathering don't necessarily happen in isolation from each other. They can happen to the same rock at the same time. Let's follow an example to see how this can happen. So in this diagram, we start with a rock that sort of looks like granite, an igneous rock with a crystalline texture. As time passes, the minerals in those rocks start to react. For example, the feldspar that was in the granite and the hornblende that was in the granite, those minerals react with water through a process called hydrolysis to produce new mineral, clay. So what was once a solid, hard mineral like feldspar becomes a soft, weak mineral like clay. As the process continues, eventually the clay is no longer strong enough to hold the still solid grains together and the rock disintegrates. And then when that disintegrated rock is acted on by a moving fluid, the finer grains of clay are carried away, leaving behind the coarser grains. Now it turns out that in the Earth's surface environment, quartz is much more stable than other minerals such as feldspar or hornblende or the other silicate minerals. And so as a result, the weathering of granite will tend to produce sand grains of quartz and clay. The clay gets washed away, the sand gets left behind, the clay accumulates elsewhere to form shale, the sand accumulates to form sandstone. Let's look at an example of where this process is taking place. Here is an outcrop of granite in Arizona. If you look closely, you'll notice that the lower part of the outcrop has a different character than the upper part, the part that was near surface. If we take a sample from the lower part of the outcrop and look at it more closely, we see fresh granite. We use the term fresh to refer to rock that has not undergone weathering. You can see that it's sort of intact, it's solid, it's lighter in color, there's no iron staining in it. What we're basically seeing is a crystalline texture rock composed of interlocking crystals of feldspar, quartz, hornblende, biotite, and maybe some other minerals. Now, if we were to take a rock a little bit higher up at an intermediate level in the outcrop and look at it closely, we see that it's much rougher. The quartz grains are still sort of standing out and intact, but what had been the other minerals has become very weak, so it's eroded away. That's because those minerals have undergone chemical weathering and have started the transition into clay. Now at the base of the outcrop, in the last 20 years, the stronger grains have broken away from the rock entirely and have accumulated to form a mass of loose debris. The process that I just described was a chemical weathering reaction called hydrolysis. There's several other kinds of chemical weathering reactions. For example, there's oxidation, where a rock reacts with oxygen and the iron minerals basically rust to form iron oxide and iron hydroxide minerals. Another chemical weathering reaction that takes place is dissolution. This typically happens in limestones, which will dissolve in slightly acidic rainwater or slightly acidic groundwater. Here we see an example of a limestone surface exposed in Western Ireland, and you can see that the joints have been widened by dissolving away the rock. The rock hasn't opened up mechanically. Simply what's happened is the joints provided conduits into which acidic groundwater could flow, and the water gradually dissolved the limestone and carried it away as dissolved ions. The uppermost part of the Earth, closest to the ground, other reactions can gradually take place over time. And given enough time, these reactions can transform the rock or sediment into what we call soil. Specifically, What happens in the upper realm of the Earth is that rainfall drops down on the surface and the water starts to percolate downward. As it does so, it picks up or dissolves the more soluble minerals and carries them down. It can also pick up and carry with it the very fine clays that are within the rock. So over time, the uppermost layer of material will undergo change. We'll have a zone of leaching where percolating downward groundwater carries away certain ions and certain clays. And we have below that a zone of accumulation where those materials accumulate. This stratified sequence is called soil. But that's not the only reaction that takes place in soil. In addition, we also have the activity of microorganisms and fungi. We have burrowing organisms like worms and rodents that stir the material around. And also, we have the deposition of organic material like dead leaves and grasses at the surface, and the emplacement of organic material underground in the forms of roots. And this organic material, when the organisms die, become part of the soil. So in sum, soil is regolith, or broken up material, at the Earth's surface that has had rainwater flow through it so that it has changed and has mixed with organic material. Now, because this process is occurring progressively over time as rainwater percolates downward, we tend to have distinct layering in soils, and these layers are called soil horizons. Given time, a soil will evolve. In fact, it may end up having a distinct series of horizons which together constitute what soil scientists refer to as a soil profile. Let's quickly look at an example as it may have developed in a temperate climate. The upper part of the soil is called the topsoil, and it in turn represents basically the area that's been undergoing leaching. Soil scientists will separate the topsoil into an upper O horizon, where the O stands for organic, which overlies an A horizon. In both the O horizon and the A horizon, there's leaching going on, but in the O horizon, there's a much greater proportion of organic material. In some cases, there may be a region called the E horizon in which there's been leaching, but there has not yet been the incorporation of organic material. Below this leached area lies the subsoil, which includes the B horizon, in which there's been a significant amount of weathering and also an accumulation of ions and clay that have washed down from above. The B horizon merges downward with the C horizon, in which there's been significant amount of chemical weathering, but there has not yet been the zone of accumulation development that we've seen in the area above. The weathered horizon ultimately merges downward into either solid bedrock or the sediment out of which the soil was derived. Now, the nature of soil horizons varies with location. For example, we get very different soils depending on climate. We tend to get fairly thin soils up in polar regions because there's not very much rainfall, of course. There's snow, which doesn't percolate downward, and also there's hardly any organic matter. In temperate climates, we get soils that go down a certain distance, and we often have a well-developed organic layer on top. In deserts, once again, we tend to have fairly thin soils, but we do have the occasional flooding events which carry certain minerals out of the uppermost area and collect them deeper down. In tropical horizons, or in tropical latitudes, we tend to get very deep soils because there's so much rainfall. There are many other factors that can determine the nature of a soil at a particular locality. For example, soils that develop over weaker rocks or less resistant rocks tend to be thicker because the rocks weather faster. And soils that form on gentler slopes tend to be thicker than soils that form on steep slopes because they're able to accumulate without slipping away. And because soils take time to form, soils that have had a longer time to form tend to be thicker and have more distinct horizons than soils that have had a shorter time to form. Now, because of all these different soil types, there are many different soils at many different localities around the world, and coming up with a classification scheme for them has been very difficult. In fact, different classifications are used for soils in different parts of the world. But in general, we can see that the soils that form in tropical regions differ from the soils of temperate regions, which differ from the soils of Arctic regions, which differ from the soils in desert regions. For example, the term oxisol is used for soils formed in tropical regions. Here, heavy rainfalls leach a lot of materials out of the near-surface realm and carry it to depth, leaving behind concentrations of iron and aluminum oxide. The term eridisol is used for desert regions, where there's relatively little rainfall and relatively little leaching. As a consequence, calcite can concentrate in the upper part of the soil and locally forms caliche or calcrete.